Ladies and gentlemen, please welcome Principal Architect, Microsoft Xbox Studios, Perry Lee.
Hello. All right, so I'm between you and lunch, but we have a lot to do here. I'm going to be talking about machine learning, but I'm also going to give you a biology class, a history lesson, a course on statistics, and just a wee bit of math. And I'm going to do this within 40 minutes, so you get what you pay for. And apparently this was free, so, take that as you wish. So let's talk about machine learning. This is going to be a little different because I'm not here to sell you something. I'm actually here to tell you where this is working and especially where it's not, and some catastrophic failures. So we're going to talk about things like cognition and world peace and all these great things. But first, where should we have been with artificial intelligence? So I got some quotes, and we're going to go back to the history of machine learning and AI, but we have to go back to 1950. And in that time frame, this was the Renaissance. This was the foundation of artificial intelligence. And these are the big players that were involved at that time. These guys came out of Dartmouth, MIT, Stanford, and other learned institutions. And Alan Newell, Herbert Simon, and especially Marvin Minsky, we're going to keep going back to this guy. They were saying that a computer using some form of intelligence would be capable of being a world chess champion in 10 years. And that was in 1958. Unfortunately, it took about 40 years to get to that point. Within 20 years, a machine will be capable of doing anything a man can. Well, it does some things, robotics, for example, but not everything. So we're still waiting for that day. And Marvin Minsky, he's the godfather of artificial intelligence, said within 3 to 8 years, we'll have a machine with general intelligence. And I really want to pick on that because he was a contributor, a consultant to one of my favorite movies. And one of my favorite movies is this movie. It's 2001: A Space Odyssey. And one of the main characters wasn't a character, it was this HAL 9000 supercomputer. And it was actually a form of general intelligence. And Marvin Minsky consulted on this film, and it kind of established where a computer would be in 2001. So hopefully the audio is working here. We're going to find out.
Dave? How you doing, Hal? Everything's running smoothly, and you?
But there is no general intelligence.
Have you been doing some more work?
A few sketches.
May I see them?
Sure.
These are all the sub-elements of AI that this machine would have to do to produce these various effects.
Can you hold it a bit closer?
Sure.
Image recognition, supervised training, learning what that image is and how it's relating to something else, an actual human.
By the way, do you mind if I ask you a
It just made a
question?
decision. Actually, this is where it went suicidal.
Well, forgive me for being so inquisitive. But during the past few weeks, I've wondered whether you might be having some second thoughts about the mission.
How do you mean?
Well, it's rather difficult to define. Perhaps I'm just projecting my own concern about it. I know I've never completely freed myself of the suspicion that there are some extremely odd things about this
It
mission.
just taught itself something.
I'm sure you'll agree there's some truth in what I say.
Well, I don't know. That's a rather difficult question to answer.
You don't mind talking about it, do you, Dave?
No, not at all.
Well, certainly no one could have been unaware of the very strange stories floating around before we left. Rumors about something being dug up on the moon. I never gave these stories much credence, but particularly in view of some of the other things that have happened, I find them difficult to put out of my mind.
Well, I don't have conversations like that with Siri. As a matter of fact, my conversations with Siri usually end in absolute failure. But this is where we were supposed to be. Where we actually are is there's actual good cases for AI and machine learning in various flavors. In agriculture, in healthcare, in financial transactions, and retail. And just some actual data, some new data from 2018, 2019, in agriculture alone, 80% reduction in herbicide use through smart planning and smart irrigation. In healthcare, we see a massive flux of medical imaging moving to AI and computer vision. As a matter of fact, it's profoundly better than a human in diagnosing some forms of cancer. In fintech, 25% underwriting loss and 20% growth in AI investing portfolios. A lot of portfolios and a lot of Wall Street firms already are moving to AI-based trading. And in retail and marketing, this is a real hot area. A 70% decrease in returns and a 30% decrease in surplus activity, inventory control, which is really important. So there's predictions of where we are going with AI. By 2020, 90% of all humanity will be interacting, not just with Siri, but either obviously or not obviously, with some kind of machine learning back-end or front-end system. There's significant growth. 85% of CIOs will run a pilot program by 2020 incorporating AI and machine learning in their business, either in the front end or the back end. Employment impact, we're going to talk about this later. And some of the careers that are growing, the careers that will diminish, and the careers that will remain stagnant. But 10 to 15% of workers will shift to AI replaceable jobs from idiosyncratic tasks. And there will be a lot of business failures. So these are areas that you need to watch out for. So let's go to the meat of this. Now, who here, by just show of hands, is kind of versed in AI and data science and whatnot? Okay, some of this is going to be rudimentary. Some of it's going to be brand new for some people, but that's the purpose of this seminar today. So I'm going to start with a history lesson of when AI had its advent and when it had its three precipitous declines. So we got to start out in 1950 with Alan Turing and the development of the Turing test. And the Turing test basically said that if you are blindly interacting with a machine, in the 1950s, this was a teletypewriter and couldn't identify the source as being a machine or a human, that by definition was artificial intelligence. Well, about 10 years went on, and a very important conference happened in 1956. This was the birth of AI. As a matter of fact, artificial intelligence as part of vernacular started in 1956. And then this guy came around. This is Marvin Minsky. He's the grandfather of AI, and he was one of the hosts of the Dartmouth conference. But he started these projects and started getting government funding for artificial intelligence at Carnegie Mellon, at Dartmouth, MIT, Stanford, and so on. And finally, in 1969, when he was working with Warner Brothers on 2001: A Space Odyssey, he wrote a very important book called Perceptrons. And this was kind of the advent of machine learning and the mathematics behind it. And it kind of is its own channel of artificial intelligence, but it's a very important one now. Now, curiously, what happened the following year is, well, they started getting a lot of funding. They got millions of dollars in DARPA grants. But Marvin Minsky wrote a criticism of his own book in 1970. And almost immediately, all funding from government, from DARPA grants and other government grants ceased. This was known as the first AI winter. This occurred from 1974 to 1984. There was absolutely no funding or interest or publications in artificial intelligence. And one of the things that Marvin Minsky said in 1970 was, he reflected on these ideas, and he said that we don't have algorithms that are sophisticated enough, we don't have memory systems that are large enough, and we don't have computer systems that are fast enough to actually do useful artificial intelligence as a general concept. Okay, well then 1984 came around, and kind of a different track of artificial intelligence popped up, and these were expert systems. The idea here was not for a machine to learn on its own, but to transfer knowledge from an expert human to a system. And this had purpose. This was used in a lot of industrial controllers. You'll see them later, and in financial transactions, business intelligence. But the second AI winner happened in 1987 and 1993. There still was not sophisticated interest or computing powerful enough to grow. As a matter of fact, this was the time when you transitioned from mainframes running expert systems to PCs. But in 1997, IBM came out and they built that computer that actually became the world chess champion. So now some kind of form of AI happened. Whether you argue it's actual artificial intelligence or just a useful program, we can debate that. But IBM came around, and they came around again about a decade later with Watson, and Watson won Jeopardy. And this was a very successful business intelligence application for doing searches in real time. But the real advent happened with Moore's Law and big data. We could store more data, we could provide it in the cloud, and we had Moore's Law that was shrinking the geometries. We could have enough memory, we had enough speed in our silicon that we could actually do something useful, and we could go back and revisit all of this foundation work from the 60s. And that's what happened. In 2012, a milestone was broken. I'll show you how this worked, called the AlexNet milestone. And this is where a kind of a test, a challenge to the research groups around the world were placed to go and recognize images, millions of images, and do it with accuracy. And up to this point, they were using traditional computers. AlexNet brought in GPUs, brought in very sophisticated hardware and algorithms and systems to actually not only resolve AlexNet, but do it 15% more accurately than any other scheme before that. And this is where we are with our technologies now. We'll look at TensorFlow, and everyone's playing it, including my company, Microsoft. So you got to find the right tool for the job. And when I say that there's machine learning, there's actually a whole realm of artificial intelligence. There's fuzzy systems and genetic algorithms. These are not really machines that are learned, but machines that are programmed. And these are used in things like computer gaming and automatic braking and PLC controllers for industrial systems. But when we go into machine learning, these are some of the really interesting sciences that are used in statistical models, basically support vector machines. I won't go into the details here, but you would apply these for things like facial recognition, handwriting recognition, bioinformatics and medical testing, testing drug and drug reactions. And then we get into probabilistic models where you look into fintech, you look at options pricing and loan approval. You look at spam filters. That's a really classic example of Bayesian systems. And then we have deep learning. And I'm going to play around with this and give you a demo of this actually working for image processing. So here we are in this scheme. And there's lots of AI. That's the thing about it. You have to find the right tool for the right job. So let's have some fun. So before we go on, let me just kick this off. How do humans learn? And I think it's really important to understand the biology of how you learn versus how a machine's going to learn. And when you start out in life, when a newborn starts out, you basically have a neuron and you have connections, synapses between neurons. A newborn actually starts out with 200 billion neurons. For the course of your life, you're going to have about 200 billion neurons. There's ways to damage it, but that's pretty static. But a newborn starts out with 15,000 connections between each neuron to neighbors. Over the next 4 to 8 years, that dwindles to about 1,000 useful paths. And that's what you're seeing here. This is actually a micrograph of neurons in brain tissue actually learning and growing, being reinforced through synaptogenesis and building those pathways. But part of the idea of building a pathway is you make others disappear. If you had all those synaptic pathways for the rest of your life, it basically is pure chaos. It's pure noise. You can't do that. So Synapses form a network, and that's what you see here. Over here is that you have a nucleus, which isn't really interesting. An axon is very interesting. That's actually where you're controlling the gate, whether or not you light up a path or not. And that's going to have analogies to deep learning. So axons are the control system, are the transistor of your brain. And to build a pathway, you have neurotransmitters. And one of the most important is glutamate. When glutamate is released, it actually builds a pathway or removes a pathway. And that's reinforced through rewards. And we'll see how that works. So when you learn something, you don't start out with a blank slate. You have initial scaffolding in your brain of how to walk, how to move. For example, when you learn to ride a bike, you were falling over, you had to establish balance, but you had an initial idea that when you pedal, you're going to go forward. You had an idea that you turn the handlebar right, something's going to happen, you probably will motion to the right. This is initial scaffolding, and it's really important. It allows you to learn, it has the plasticity to make a brain do things that you naturally haven't done. Now, if you don't use it, you lose it. This absolutely happens within these pathways. If you don't reinforce these pathways, they will disappear. So, how do you retain something? And I thought this was an interesting graphic here. So you learn something. Here is the percentage ability of how you can successfully learn something as a human. So the best thing you could do is learn by doing. You retain or build more synaptic pathways by actually applying something. So if you participate, play exercises, if you go to a workshop, or if you are in active discussion with me, you're going to retain that. You hear it, you see it, you have other senses that are contributing to that pathway. That's about 20 to 75% retention. On the receiving end, me talking to you right now, there's a 20% chance you're going to forget, 80% chance you're going to forget everything that I just said. And that's fine. I'm standing between you and lunch. So this is how you reinforce something. And it has analogy to how a machine learns. We'll see that in a second. This is interesting. UC Berkeley came up with an experiment, and they got several hundred candidates, test subjects, to go and play a game. This is a game called Montezuma's Revenge. And what they did was they let 100 people play it, and they figured out, well, how long would it take them to finish the game? So if they see the game normally, it took about 5 minutes. Then they started altering things, the physics of the world, what the machine looks like. Matter of fact, let's go play this for a second here. Let's go here. So in Montezuma's Revenge, you know that you have an arrow, right? I knew to go to the keyboard, left is left, right is right, up is up. You kind of know, okay, well, there's a pit next to me there, something bad will happen. Oh, I just learned something. So it takes about 5 minutes for a human to figure that out. Well, that's great, but if you change your prior knowledge, if you start altering that initial scaffolding, well, the whole thing changes. And humans actually didn't even want to play this version of the game. This is the game that they were playing. And it's hard to know what anything is. What does any of this mean? But for a machine, it's irrelevant. It's just pixels. And in all cases, it certainly took the machine to master the game about 37 hours. But it actually did that in any case. So there's initial scaffolding or initial bias that's built into human biology. So this is the analog. If you look at a human brain cell, you have the nucleus, you have a cell body, you have dendrites picking up other connections, you have the axon, which is the gate, which is right here, and you have synapses that span out and form those connections. So in machine learning, the analogy here is that you have an activation function. This is, without going into the details, it'll look like a tangential function or a stair-step function like this, but that's the gate. So when you build a large neural network, this is AlexNet, You take an image and you're cropping it, and you go through convolutional layers of this network until you finally get to a fully connected layer at the end, and it outputs a label. And if they get it wrong, you say, you're wrong. It'll retrain. It'll reinforce the pathways that are relevant and decrease the pathways that are irrelevant. So in machine learning, just some vernacular, there's two ways you could do this. You can classify an object like I just did, a lion, a bear, tiger, whatever. In this case, you're classifying red dots and blue dots. And you divide them up, and basically that's called a hyperplane. The other way to look at machine learning is regression analysis. This is, go back to your statistics 101, this is pure regression, finding the pathway of a curve. But it gets more complicated because these are really easy to discern. I'm going to show you some examples that are very, very complicated for a machine. And there's two types of ways that a machine is used, a machine learning-based device. There's a training phase, and basically you take an image, a training set, you push it through your network, and if you get it wrong, you can supervise it, that's supervised training. You could say that, no, you're wrong. And it will go back, it'll back propagate and reform that network with those appropriate weights. If at some point you're satisfied that you reach 90% accuracy in your training set, well then you can release it and run it in inference mode. And basically this is a much faster path, and it's the used path, for example. So I'm going to show you TensorFlow. This is a little demo of it. But it kind of reinforces how this works. And I'm hoping it actually fails, because it really fails in some spectacular ways. But there's some vernacular here. I don't know if the slides will be published or not, but there's a QR code up there. You can go and start playing with this. But I'm going to be training a system to go and find spirals. And the activation function here, this is that axon. I'm just going to use a tangential function to say that this is a reinforced pathway or not reinforced. A really important thing here is the learning rate. So the learning rate controls how fast you learn or how accurate you learn. And you can overfit a model. You can take a training set where you want to identify, brands of shoes. But you might train it only for, your training set might only have Nikes. You introduce an Adidas in there, and when you're actually using it, if your model is overfit to only recognize Nike, you probably won't see an Adidas as a jogging shoe or a running shoe. So you have to be very careful of the learning rate. And you also have to be careful of the features. The features are what you initially start with. These are going to be things like edges, curves, very small areas of images, or in speech, it might be phonemes, or in spam email, it might be words or grammar. You don't actually introduce a machine to say, this is a picture of Perry Lee right from the start. You want to look at different aspects of the person. So let's look at this. I'm going to go over to TensorFlow and see if we can light this guy up. Okay, so what you see here is a spiral. You knew that this is a spiral, right? But if you were starting out as a newborn, you probably didn't know. This is a newborn, and I've purposely selected primitives, basically horizontal lines, vertical lines, a set of primitives, to actually go and build a spiral out of these primitives. There's a hidden layer, the stuff in the middle, and then the output. And what you want is an output. What you want to be looking at is that test loss. You want a system to be fairly accurate. This is about 50% accurate, so it's a dice roll. And that's not going to cut it. So if we, let me go over here. We start it up. I'm hoping it fails. And you can see what it's starting to do. look at the pathways. By the width of the pathway, you can see which pathways are reinforced and which ones aren't. And I can hover this over here and say, oh, that's a pretty strong weight. You can see what it's doing here. It's kind of building up these set of primitives together to build up further sets of primitives or subprimitives until you finally get to something that's not a spiral, but it's kind of getting there. So our test loss right now, we're getting about a 9.6% test loss. And that's not bad, but after about 500 iterations, this is what it resolved to. And this is why machine learning is really tricky and can go very wrong. And I'm going to show you some examples of where this fails. But it's kind of normalized on this. It says, these are the traits of what I'm going to call a spiral. And that's great. Spirals are kind of hard. If we change the working set to say, well, go find a set of dots, blue dots in the middle and a ring around it, this is going to be pretty easy. And it resolved. Very easy. But it's all up to the features and it's up to the correct learning rate and the correct activation function that you use. And this is another example. Here there's two sets of clusters, and it's trying to divide that hyperplane to define what does this mean. But this is how most machine or deep learning systems are going to work. So if you're running a business and you're using this for retail marketing or future pricing, how do you measure this? Well, you have to look at that training. That training wasn't accurate, so you have to specify how accurate do you want to be in your model or your output, and how fast, how many iterations you're going to train. And you can see that training back in the day using AMD and Intel CPUs were 1 or 2 orders of magnitude slower than what you can do now with GPUs. The duration of the training is very important as well. There's loss and there's the number of training iterations. This is an art. This is where your data scientist comes into play and says, you've overfit a model. You're training it too hard for your data set, or you've underfit it. You're learning very well, but you're completely inaccurate. So there's a balance here. You want to establish basically a good rate of learning, less loss, and you want to train it over the shortest time possible. And finally, the accuracy, that 90% that I was trying to achieve. This is AlexNet, by the way. This is where AlexNet went from an error rate of about, 28%, and they got into 11%, 12%. I forgot what the actual number was. But that was that stair-step function that introduced deep learning to the world. Now these are some failures. So if you take a machine learning exercise classifier for that spiral that I just showed you, and you use this for a self-driving car, this is an interesting analysis that was done. By placing electric tape on a stop sign, above it and below it with words love and hate, 67 to 100% of self-driving vehicles, for the ones that exist, interpreted that as speed limit 45. And in this situation, you can actually train with adversarial samples. You could take very slight changes to an image and place that in your training set. And when you do that, this set of 4 assault rifles resolved to a helicopter with 78% confidence. And this is my favorite. This was an example for retail marketing where they used, I don't think it was a neural network, but it was basically a name generator. I guess it was a neural network. It was trained to find pleasing words. And it came up with Clardic Fug, Bunflow, and Bank Butt as swatches for paint samples. So you can't let this thing just run by itself. So let's go into some impact here. I mentioned the job impact. World Economic Forum predicts by 2030, 30% of all jobs will be affected, either positively or negatively, or there'll be some kind of transition. over the next 3 years, and this was in 2018, AI will eliminate 75 million large cap jobs worldwide. That's a 10% decrease in employment. But you also see the corollary, an 11% increase in new trades, in new occupations. So what are these occupations? Well, there's things that have historically been affected in employment, factory and assembly. Over the last 50 years, that's been true. Data entry, clerical occupations, call centers are a big thing. There's a lot of chat bots now, and some market analysis. On the right-hand side are the growth areas. So we know about data science and all that. That's a growth occupation, emerging tech specialists, but there's also these nebulous positions that, kind of came out here, like artists, teachers, things that are not really satisfiable or human satisfiable to be replaced by a machine. There's been attempts for machines to write music, write books. So far, that's met with a lot of reluctance and failure. But in the middle are some really interesting areas that will be affected. Not in growth, not in decline, but the way you do your job. So lawyers and the legal profession. So in 2017, an AI system achieved 94% accuracy in financial law, in legal analysis. And this is compared to an 85% accuracy with humans. In the health industries, we already know that there's a wealth of data that hasn't been used. A 2018 NIH study found that AI is much more accurate in finding forms of cervical cancer. There's also research that came out that finding malignant melanomas and other skin cancers are profoundly more accurate using machines rather than humans. Accounting and finance, I talked about that before. AI has improved ERP system speed and accuracy by 86%. And even in the engineering professions, if you're involved, say, with electrical layout, new tools and new CAD flows are being built by big EDA players that essentially do that job. Now, what that means is that these are not necessarily areas that will see a decrease in employment, but they also won't see an increase in employment. You'll be doing more with less, but AI will be the tool you use to do more. Now, what's interesting is the federal investment in AI, and I'm building this out so the teasers last. And you see, spot, 80 million here, 12 million there. Russia really hasn't invested much. Taiwan, 300 million. When we get to some of the big players that actually have national policy and funding, we started introducing South Korea. And they have a 5-year plan with $2 billion spent to build AI software and hardware. The European Union has built a very comprehensive plan that you can find online in 2018 with 500 million already spent with 2 billion in the funnel. And France alone has their own 5-year plan with an additional 2 billion on top of that. We look at the United States. Right now, 7 billion is appropriated for unclassified military spending. And $0 has been appropriated at a federal level for non-military spending. This is a correction. Last week, the administration actually has a plan, but there's no additional funding. There's a plan to persuade our national labs to direct more focus or energy into AI programs, but there is still $0 of non-military spending at a federal level. The big player, of course, is China. They have in 2017, they have a very well-written paper and funding in the channel with 2 billion already spent, with 200 billion spent by 2030, with the intent of being the world leader of machine learning and artificial intelligence, not only grown domestically, but to attract companies and talent to China. So you came here, if you're running a business, how do I incorporate this? So let's talk about that a little bit. So 2018, 75% of AI pilot projects have underwhelmed expectations. This is from Forrester Research. And part of the reason is that they haven't developed a strategy. And the strategy is comprehensive, but it starts with your data. All this AI is built on data, and we have the ability to have big data and large data sets. But you have to have a data strategy. You have to understand, what tool do I use to build models? It might be a set of tools. It might be a neural network or a recurrent neural network. It could be a Bayesian network if you're doing statistical analysis. It could be a fuzzy system if you just need an automatic break. Data security and identity policies. So you have a lot of data. Microsoft takes this absolutely seriously of what data is retained and what data can be used. You need to do the same thing at your corporate, at your business level as well. Who owns the data? If you're building an IoT system and you start accumulating data from a number of different sources, you have to have that discussion of who ultimately owns that data. You have to build and retrain your AI workforce. So if you're on the receiving end, if you're in the legal profession or medical industry, you're gonna be doing more with less. So there's a retooling of those occupations that has to occur. And probably the most important is calibrate your expectations. One of the reasons there's a lot of failures is you use the wrong tool for the job, and it comes out to be no better than rolling a set of dice as to how your machine vision system works in the end. You have to calibrate your expectation as to what is an acceptable loss. A machine isn't gonna be HAL. It's not gonna be this foolproof supercomputer. It's as good as your data and as good as your training of that data. And of course, there's data warehousing, visualization tools, and labeling your data. It's really important not just to take all your data, throw it into a data lake, and hope for the best, because you're gonna have to revisit that to build a successful model. So that was a lot of details, but generally speaking, more data is better than less data. You can see it here is your accuracy. Your accuracy definitely improves as you scale your data. That's pretty obvious. I talked about using the right tool. That one chart, that ring with all those AI tools, data science tools, there's no one tool to do the job. Manage your data, hire a data manager. Use different models as a collective. It's good to have adversarial or generational models that actually play against each other. And of course, don't overfit your system. If you train to only identify Nike sportswear, that's all you're gonna see. So, I always like to leave a discussion of what's next. This is from Gartner. This is the hype cycle. If you've never seen this, these are technologies. All technologies there's a lot of hype, inflated expectations, and then you start to realize, this didn't work in my pilot, and then this is where it actually takes off. These are where technologies become mainstream and profitable. So we're on the the precipitous slope in the trough of disillusionment for machine learning and deep neural networks, computer vision. And within 3 or 5 years, they're gonna become absolutely mainstream and integral to a number of jobs. The interesting ones are the ones that are creeping up. The ones I wanted to focus in on are prescriptive analytics, deep neural network ASICs, and platforms, especially cloud platforms and different tools like AI developer tools. And I wanted to go and poke at that artificial general intelligence one more time. So, prescriptive analytics. This is gonna be really interesting because I think this is part of Industry 4.0 and all that and the whole IoT buzz, is that you don't have a system or a collection of systems now just telling you something's wrong or predicting that something will go wrong in 10 minutes, but actually prescribing a set of events that can change the problem or make the problem never occur. I think that's very interesting. I also think new hardware, there's quite a bit of it. IBM's heavily involved in neuromorphic computing, and There's a lot of work in deep neural network ASICs and chipsets that can radically change the training and the inference, making it faster and use less energy. So you can actually start thinking about appliances using these technologies in a very low-cost way within a cell phone, but even within a very simple device. And platforms, like platforms as a service and AI toolkits. I played around with TensorFlow, but this is what's going to really make it, because software rules the world. And if you make it easier to build these models and run these models, it's just going to gravitate and precipitate to other industries. But that artificial general intelligence, that's HAL. That's where you're having a conversation with a machine and it attempts to kill you at the end of the day. I think we're a very long ways away from having that as a reality. There are inherent philosophical and technical issues with understanding or have a machine operate at that level. And there's been tragic failures trying to get to that point. And that's it. So I'm Perry. I'm going to be here for about a half an hour, then I need to run. But I'm with Microsoft, but there's two companies I founded that I want to give kudos to that are involved in these areas. All three of them are. That's it. I think I got about 12 minutes, maybe less, but I can entertain 2 or 3 easy questions. Oh, only hard questions.
So, to sum up your view on this, what was your philosophical opinion on all this and how it's going to transform us?
The question was, what's my philosophical opinion? Oh, well, that's a can of worms. So the ball's already rolled because there's industries that already see the benefits. If you're in an industry and you haven't implemented machine learning or AI or haven't built a big data or understood the value of data, then you're already at a loss. So you're not gonna withstand the economics or the trend. Now, what I believe is going to happen is that AI is going to find itself in areas that people may or may not disagree with. There's $7 billion already in funding in weaponizing AI. I've already seen devices that, drones that actually carry a single round, making a decision of whether to shoot or not. So there's a lot of AI out there that is going to be debated at a national or ethical or moral level. But economically, it makes sense to do this because, especially in industrial IoT, which is an area I've been looking at, there's hidden information within the data. And when you have enough data, you can start understanding trends in a large system. And the effect after applying these tools isn't going to be a 50% reduction in surplus or a 50% reduction in downtime. It's going to be these incremental single-digit increases, a 4% lift in worker safety. And that could be a very big thing for these large multinationals. Any other questions? Yeah.
So who do you think is a leader in hardware? So I know NVIDIA's been heavy duty to it, but there's Amazon doing a few things.
Yeah, so the question was, who's the leader in hardware? So NVIDIA had a lot of growth last year. Part of it is in data centers, but also in cryptocurrency mining. But they're very successful in performing this matrix math. All of this is just matrix math, and it just works itself out for a GPU. Google has their TPU. The TPU is, it's a tensor processing unit, and it's made for this type of work too. The up-and-coming hardware, emerging hardware, are things like synaptic phase change memory from companies like Mythic AI in Austin. And IBM has been working probably about 5-7 years on their neuromorphic machine called True North. This is a spiking neural network that you can build within hardware and silicon, essentially kind of like a phase change memory. And there's lots of startups. There's another talk I give on these emerging hardware systems, but those are the big players, I would think. Yes, sir.
How do you build in acceptance and trust of the outcomes? Like the outcome is based on reliable data, or it's valid. Like I want to believe the prediction, or I want to say, what's the weather going to be tomorrow, and run this test, or what's the environment on Earth going to be like in 50 years? And I want to believe the outcome.
Right, and that's where these techniques like retraining your system when there's errors. There will be errors. You know, humans are lifelong learners. A machine can't be static. It has to be retrained and retooled. Techniques like adversarial systems, where machine learning systems play against each other. You have one system that's trained and another system that's trained on a different set of data. It's like bringing in multiple cultures within an organization to arrive at a common answer. But to get to your point, when do you know when you're good enough? Well, as an organization, you have to think about your customer and how your system you're building is going to respond to their environment out in the wild. And that comes with, getting to that confidence level, that 90% level, that you're not always going to be right, but you want to be right most of the time. Humans aren't always right. So if you're building a system based on trust, and let's pick a good one, self-driving vehicles. You got to be spot on, right? I mean, this is, we're talking about lives here. So there's been systems that have been built like autopilots. They're a little simpler. There's usually no one else flying in front of you, but there are automatic systems and machine systems that we trust on a day-to-day basis, and that'll come with time. And that'll also come with retraining and retooling and learning from new data sets. Continuously collecting data, retraining your models, and building adversarial models that can play against each other. Anything else? One more. Yeah.
Any other industries that you see besides the ones on the slide that are ripe for disruption? The one that comes to mind is Lemonade Insurance Company. It's a AI-based, make the claim, 2 seconds. Allstate was worried about them making commercials without a robot's going to adjust your claim, but the Amandus model of take out that broker middleman. You brought up legal, accounting. If you had to put your money on the most disruptable business besides those, anyone come to mind?
I think retail and marketing are going to be huge, because trying to find the customers, going on social media and identifying what kind of clothes you wear, going in within Target, for example, and figure out, oh, you're there, you're hovering around, the bathroom tissue aisle, so I'm going to artificially raise the prices on you. There's lots of ways that you can actually capitalize with AI tools and automated tools like that. So I think where the money is, that's going to be a heavy growth industry. So fintech is already on that curve. I think retail is broaching that now. All right. Thank you.